Well, we're here back again, and now Jessica Fintzen will speak on representations of p-adic groups and applications from Cambridge University, Duke University, and the IIS.
Thank you very much. Thank you very much for the invitation to speak at this conference. I'd like to make two announcements before I start the math part. First of all, I'd like to encourage everyone to please turn your camera on. I really wish I could be now in Valparaiso and see everyone. So it would be great if I can at least see you on the video. Thanks. And in particular, students, I encourage you to turn the camera on. It helps you to be seen as well. Oh, great, much better. The second announcement is I'm sharing my slides now in the chat. Obviously, I prefer if you listen to my talk, and if you have questions, feel free to just interrupt, ask questions, or write questions in the chat. I try to look at the chat, but I can't promise that I see everything. The reason I'm sharing them is because when I'm listening to talks, I prefer to have the slides as well in case I want to go back to check the notation. I've designed the slides so that hopefully this is not necessary, and you're welcome to just ask, as I said, but here they are. The main motivation for sharing them is that I hope that every other speaker will share the slides at the beginning of the talk as well as a consequence. All right, so let me start with the math part now. So what time is it? 5 past. All right. So I was told that the audience is rather broad. We have some people interested in representation theory, some interested in number theory. So I hope that everyone can get something out of the talk. Some parts might be known to representation theorists, but I hope everyone will learn something. And the idea is that I want to tell you about what we know and don't know about the representations of p-adic groups, and then show you how we can use this actually to apply it to number theory, to also obtain results in number theory, for example, to obtain congruences between automorphic forms. So I hope to have something there for everyone. All right, so that's the topic. Let me begin. So the notation for this talk will be that F is a finite extension of QP or the Rowe series over a finite field. So it's a non-Archimedean local field. It contains a ring of integer O, a maximal ideal P, and then we have the residue field FQ. And so the main player, the main object of interest is denoted by G, which is a connected reductive group over this local field. So for the students that might maybe not be that familiar with reductive groups, just think of, for example, GLN or SLN, or think of those matrices that preserve an inner form SON, or those that preserve a symplectic form SP2N. And everything that I tell you should make sense then for you. So you should get a feeling for what are the objects, what happens. And sometimes I talk about general representations, then just think of all these together and more crazy examples. So in general, you can associate reductive groups are very similar to Lie groups. So you have all these types for Lie groups, like the exceptional types. And for those, you also have reductive groups, but you don't really need to know how they look like to understand this. So what do we want to do? We want to construct all the representations of this p-adic group G. So I often call it G a p-adic group, even though it might be over the Laurent series over finite field. And I put in some adjectives. So I want to look at complex representations, so map from G to the space of automorphisms of a complex vector space. And I look at the irreducible ones, so those that only contain itself, and the trivial representation as sub-representation, precisely these two, just to focus on the building blocks. And I add the adjective smooth, which means that we get a more reasonable category to work with. It means that if we look at a vector in this vector space on which the group acts, the stabilizer of this vector should contain an open subgroup. So the stabilizer of every vector should be rather large, so that a lot of the group fixes this vector so that some of the representation doesn't get too crazy. The representations are still usually infinite dimensional, so it is a complicated situation, complicated representation, but we get a reasonable category to study and to work with. And so when I say open, I mean these groups, these p-adic groups have a topology that comes from the topology on this local field, which comes from the p-adic absolute value. And some people like to also look at representations that have FL bar coefficients, where I restrict to the case that L is a prime different from P. For example, if you want to look at the local Langlands correspondence and family, you are interested in what happens if the coefficient field has a characteristic different from 0. All right, so that's the motivation, the long-term goal. But why do we care about this goal? Because there are tons of applications. For example, there are applications to the representation theory of p-adic groups themselves, which is not surprising. If you want to study, for example, how a representation behaves when you restrict it to a subgroup, which is often called distinction, the question if it contains a trivial representation or not, for example, you need to understand how these representations look like. And the easy way to understand it is if you're able to write it down and to construct it explicitly. Other questions you might want to study is the Hauer correspondence or theta correspondence, how do representations translate between different groups. You might want to calculate explicit Harshchandra characters of these representations. And for all these questions, you need to know how to write down the representation. So that's why being able to construct them is really crucial. There are also applications beyond. For example, not surprisingly, if you want to write down an explicit local Langlands correspondence, you need to know how to write down representations. So an explicit Langlands correspondence means that you take an explicit representation, so you better know how to write it down, and associate to it a representation of a Galois group or something very close to that, a Langlands parameter. So if you want to do it explicitly, you need to know how to write down these representations. But then there are applications also beyond the local theory, for example, to the global Langlands correspondence via automorphic forms. For example, in a joint work with Sug Woo Shin, which I'm going to talk about towards the end of the talk, we obtain congruences between automorphic forms. And this has then applications to, for example, the global Langlands program. There are also applications to p-adic automorphic forms or the p-adic Langlands correspondence. And I put a ... here because I hope that you'll find yourself more applications. So maybe you go out of the talk and realize a new application. There have been all kinds of crazy applications. For example, these representations have been used to prove instances of the mirror symmetry conjecture as well. All right, so these are just some possible applications. And now I want to dive into the representation theory. So I said that's our goal. We want to construct all these representations. And how do we do this? We use certain building blocks, which are called supercuspidal representations. Or in the FA bar setting, they are called cuspidal representations. And if this is the first time you hear the word supercuspidal, or if you heard it before and got scared of it, you shouldn't be scared. It literally just means building block. It means that if you take an arbitrary representation, you can embed it into the parabolic induction of a supercuspidal representation of a levy. And parabolic induction is something you can write down. It's a space of functions you can write down, while the supercuspidal representations are very mysterious. Those are the ones that don't occur in a proper parabolic induction. And it took mathematicians a long time to be able to actually write them down. So the story started roughly in the 1970s with work of Howe and Moy, and they looked at the case GLN and tried to construct representations of GLN. And then about 25 years ago, the story was finished by Bushnell and Kutzko, and they gave a construction of all the supercuspidal representations of GLN. So for GLN, we basically know how to write down everything. It's a book somewhere in the background on the shelves, so it's not I can't do it in a minute or so. It is quite some work, but we know how to do it. And shortly afterwards, Marie-France Vinares observed that actually the same works also mod L. So I write in blue the mod L and in black the complex story. And then the next groups that people looked at were the classical groups. So these are fixed points of an involution inside GLN, so orthogonal and unitary and symplectic groups. And Sean Stevens showed in 2008 how to obtain all the supercuspidal representations, basically using the story for GLN and trying to make everything behave well under the involution. That's easier said than done. There was a lot of work that had to be done there, of course. And then recently, Corinne and Stevens showed that the same works mod L as well. And we also know how to deal with inner forms of GLN thanks to the work of Secher and Stevens roughly around the same time in 2008. So inner forms are, for example, units in a division algebra. And we can treat them in a similar way. So this leaves the question of what do we do in general for general reductive groups all at the same time, and not just those that we can reduce to the case of GLN. And that's the main focus of the first half of my talk. So what are the constructions for general groups? It started with Moy and Prasad in 1994-96, and they introduced the notion of a depth. A depth can be either 0 or a positive real number. and it measures some of the complexity. I said earlier that a representation is smooth means that every vector is fixed by some compact open subgroup. But this compact open subgroup, or this open subgroup I said, but it can be compact open, this compact open subgroup can be very, very small. And the depth is a measure of how small it gets. So the smaller it is, the deeper is the representation. And I want to draw for you a picture now of what we know. So I want to draw the representations with the corresponding depth in one direction. And in the other direction, I want to draw the prime number p, like 2, 3, 5, 7, 11, and so on. This is the residue field characteristic of the field that we work with. So it's the p and p-adic groups. And some results depend on what prime we work with. And so what Moy and Prasad did is they classified all these depth zero representations. And Morris did the same roughly around the same time. So I listed Morris there as well. What do I mean by classifying? They said that depth zero representations are essentially representations of finite groups of Lie type. Of course, then you have to study representation of finite groups of Lie type, which is a very complicated question in itself that Deline Lustig and Lustig worked on. But the idea is that we can reduce the depth zero representation to representations of finite groups of Lie type, so representations of finite groups. And so then the question is, how do we go beyond this picture? How do we get representations of higher depths that lie down here? And so that started with work of Jeff Adler in 1998. And then 3 years later, JKU generalized Jeff Adler's construction vastly. And we get all these blue dots here. Each dot represents a representation. So these are representations of positive depths that are swimming down there in the diagram. And so JKU's construction is construction that basically everyone uses nowadays. When I say that we need explicit construction to write down a local Langlands correspondence, to study distinction, to study the Howell correspondence, all these things rely on JKU's construction. So basically, everyone who wants to work with general groups and make general statements tries to use JKU's construction because that's the most general construction we know today. And so then if everyone uses it and we know a lot about it, it would be nice to actually know what do we get out of it. And so that was partially obtained by Julie Kim in 2007. Julie Kim proved that Yu's construction provides us with all supercuspidal representations if we are in this region over here where the prime p is very, very large, and if the characteristic of the field f is 0. So if we work with a finite extension of QP, not if we work with a Laurent series of a finite field. In that case, we get everything in the region where p is very large. And I guess the natural, so that was a big result. That was great, awesome. Now everything we prove for Yu's construction works for every representation in this region. But then you might ask, what about her conditions? Can we do better? In particular, you see there are not many dots here. So is there something else out there? And so this was partially answered by Vida and Yu. So they gave a new construction of some representations, which I've circled here with yellow circles. And they called the representations they constructed epipelagic representations. Why did they construct so-called epipelagic representations? Or why did they call them that? It's because Mark Vida told me that he thinks of representations as fish that swim in an ocean. And if you look at oceanography, the upper zone of the ocean is the epipelagic zone. So if you think that these are all the representations we have to find, the representations that Vida and Yu found are the representations in the upper zone. And that's why they call them epipelagic. So these are representations of smallest positive depth. And so what Vida and Yu actually did is they said, okay, let's take a certain input. And the input are so-called stable vectors in the Moy-Prasad filtration. Doesn't really matter what it is, but say there exists a nice input, then they perform a construction, and the output are some epipelagic representations. But they could only prove that the input exists for large primes. And so what I've shown partially in joint work with Beth Romano in a special case is that actually the input for Vida and Yu exists for all primes, also for small primes p if it exists for large primes. And so this means we get new representations down here for small primes p, and these are genuinely new representations. So we get some actually new representations for small primes that do not arise from used representations. And you see something funny, actually. There's sun right now on my face, which is very unusual because it was overcast the last week. So you should enjoy the sunshine indirectly. So that means, back to the math, that there are new representations, and the question is, what else is out there? But this is a very complicated question, so I'm not able to answer this for you today. This is what I'm working on, and hopefully I'll be able to tell you more in a couple of years, but it's really complicated for various reasons. So this is work in progress. What I would like to tell you about is what we know nowadays, what's the current state of the art. And this is the following region, the region that P is large. So look, there are a lot of blue dots here, even though there's no exhaustion yet. But so maybe we can get exhaustion in this region where P is large. Maybe we don't even need it to be very large. And this is indeed true. We can get exhaustion in this region. So that means that everything that's proven for use construction only relies on P large, not P very large, which is really a big difference sometimes. And moreover, we can remove this assumption that the characteristic of the field is zero, which was an assumption that bothered us a bit, because why can't we work with function fields, with Laurent series over a finite field, localization of function fields? And yes, we can. We get exhaustion in that region as well. So this is the result that will appear next year in the journal. It says that suppose that the group G splits over a tame extension of the field F. Why do I assume that? I assume that because JKU makes this assumption. Basically, everyone makes this assumption. Not everyone, these small yellow dots here exist also in the non-tame setting, but most people make this assumption because otherwise it's getting very difficult. What does it actually mean for the group to split over tame extension if you haven't heard this terminology before? For example, if you work with units in a division algebra, to say that this group splits over tame extension means that this group becomes isomorphic to GLN over a tamely ramified extension. And for division algebras, this is of course the case because we know that's a known result that this is always the case. But for more complicated groups, this might no longer be the case. So we make this assumption, and then we assume that P doesn't divide the order of the Weyl group. What does this mean? It means, for example, for GLN, the order of the Weyl group is n factorial. It's this case here. So we want the prime to be larger than n. And in general, for classical groups, we exclude all the primes up to n. And for the exceptional groups, in the worst case, we exclude 2, 3, 5, and 7. So we actually don't exclude that much. And that's what I mean with P large, just these few primes are excluded. And under this assumption, use construction provides us with all supercuspidal representations. And the same actually works also mod L. So an analogous construction works mod L as well. And I should maybe make a remark that maybe someone comes and proves that we get exhaustion in general. Of course, this cannot happen because of the yellow dots here. And I expect in general that this assumption that P doesn't divide the order of the Weyl group is optimal. I put a small star here because to make this precise, you have to look at all inner forms at the same time and at types, not just supercuspidal representations. The details are in a paper that I wrote in January 2018, put it on the archive then. That's the motivation why I believe it's optimal in general. So that's a bit hand wavy, but that's why that's basically the best we can hope for in general. All right, so that's the state of the art, at least the state of the art we want it to be. There was a small problem, which is that recently someone encountered that JKU's proof that his construction really yields supercuspidal representations does not work. So whenever we work with used representations, we assume they are supercuspidal. And now the proof shouldn't work. More precisely, JKU's proof relies on a typo in a reference. An old paper from the 70s from Jordan was like the times I think where mathematicians wrote papers by hand and the secretary typed it. And in this paper, there's a plus minus 1 missing in a statement. It's just a plus minus 1. But if you put the plus minus 1 back into the statement and then go through JKU's proof, the whole proof breaks down. It doesn't work anymore. More precisely, there even exists a counterexample to the key ingredients of JKU's proof, which are, doesn't matter if you don't know what they are, just for reference these are proposition 14.1 and theorem 14.2 in JKU's paper. Doesn't really matter what they are. These are statements about spaces of inner dimensions of spaces of intertriners. Whatever this is, it doesn't really matter. It's important. This was the key argument. And not only is there the typo making the proof no longer work of this key proposition and key theorem, this key proposition and key theorem is just false. So that was a bit scary. Like, what do we do if everyone used construction? Everyone assumed these are supercuspidal. So I guess I wouldn't give a talk about it if we couldn't fix it, because otherwise we would all just sit here and cry together. So luckily, it's actually not a problem. Use construction still provides us with supercuspidal representations. His proof doesn't work, but there's an alternative proof. So I use the first half of this proof, which goes through, and then the second half I substitute by 3 pages on my own. And then we get a valid proof to show that his use construction provides us with supercuspidal representation. So we don't have to worry. This is actually the setting. This is the state of the art. That's what we are at now. All right. Let me just pause for a second, let everyone breathe. That's the situation we are at. That's the current picture. What I would like to do next, unless there are any questions now, I want to give you an idea how to construct these supercuspidal representations. I want to like to add a few more details, a few more recent results that happened in developments around these theorems and how to fix them. And afterwards, I want to move on to show you applications to number theory. All right. So how do we construct these representations in general? There is a folklore conjecture that they constructed in a 2-step process. The first step is that we construct a representation of a compact mod center open subgroup of the group G. So for example, we construct a representation of SLN ZP inside SLN QP. And then the second step is that we just compactly induce this representation to build a representation of the group G from this representation rho. The second step is something well known. So the difficulty really lies in trying to find the correct compact open subgroup K with the correct representation rho K, so that we get what we want. And so this is still very abstract. So I want to make this more explicit by showing you an example. So let's just work with the group SA2. And we need a compact open subgroup. Let's take this compact open subgroup consisting of all the matrices with 1 plus P on the diagonal, P in the upper right corner, O in the lower right corner, and we take the plus minus 1 as part of it as well. And so we need a representation of this. So I want to choose a 1-dimensional representation, so a map from this compact open subgroup to GL1, so of C, just to C star. And so what do we do? With the plus minus 1, we just send to 1. And I need to tell you what to do with the rest of this. So I have to tell you what to do this compact open subgroup. And so this compact open subgroup is not an arbitrary compact open subgroup. It has a name, which is written here. So this might not tell you too much. So let me see if I can actually close the curtain a bit so you can see me again. Sorry. What is this? So this is part of this Moy-Prasad filtration. Okay, now you ask me, what is the Moy-Prasad filtration? So let me start with analyzing what these objects are. So this X, what is this X? This X is a point in the Burat-Tietz building. So what is the Burat-Tietz building? The Burat-Tietz building is a lot of real vector spaces glued together. And it has an action of the group. So in the case of SA2, it's a lot of lines glued together. So a lot of lines that are glued together. So where are the lines? So for example, here's a line, and another line is here, and another line is here. So a lot of 1-dimensional vector spaces glued together. And so then we can, if we have a building like this tree here, and the group acts on it, it encodes some information. So for example, we can take a point. So let me take this point, call it X. And now what information does this point encode? It encodes, for example, the information about a subgroup of the group that fixes the point. So we can look at the stabilizer of this point X. And so this stabilizer is basically, or in this case, it's the subgroup that has O on the diagonal, P in the upper right corner, and O on the lower right corner. And this is what I like to denote by GX0. So this is the zero filtration subgroup or the parahoric subgroups. I've written a trigger here because in general, GX0 might be off by a center or finite index from the stabilizer. But the idea is that the parahoric subgroups are up to small details, the stabilizers of points in this building. And so all the elements of the group that fix this point when acting on the building. And now I said there's something called a Moy-Prasad filtration. So what is this? So instead of just fixing this point here, we can just fix more and more. We can fix a ball of, say, radius 1/2, or a ball of radius 1, or a ball of radius 1/2, and larger balls. And the more we fix, the smaller does the group get. And that's how we obtain a filtration. And this is roughly the Moy-Prasad filtration. So in this example for this point, if you look at the filtration corresponding to a ball of radius 1/2, so I should say I'm slightly lying. This is really the way to think of it for you. If you want to make the precise definition, there are some more details you have to look at, but just think of it fixing balls of larger and larger radius. And so at 1/2, you get the subgroup that has 1 plus P on the diagonal, and P and O on the off-diagonal terms stay as before. And then at depth 1, what you get is that now the diagonal stays as before. It's 1 plus P, and now the off-diagonal terms, they get slightly smaller. And so that means in general, you can define this filtration here by basically, you see you alternatingly change the diagonal in the first step, and then in the next step you change the off-diagonal, and the next group would be changing the diagonal again, and then the off-diagonal and the diagonal, and so on. And actually it's defined for all real numbers, but I only wrote the groups that are of interest. So for example, if you look at a ball of radius 1/4, it's the same as looking at a ball of radius 1/2. These groups will be all the same. And so this is the Moy-Prasad filtration. You can do this for all groups. And this filtration is very important when constructing representations, or for example, when defining the depths. We said the depth is defined by how far do you have to go down in a filtration of compact open subgroup until you find fixed vectors. And this is the filtration you look at, the Moy-Prasad filtration. You can define it for every point in the building, but if you basically, this is the prototype, the other point of interest would be this point here, where you just get the normal congruence filtration. So you got all the matrices congruent, 1 mod P, 1 mod P squared, 1 mod P cubed, and so on. So basically you have seen all the filtrations for SL2 up to conjugation and slide shifts and where jumps happen. And so now I want to use them to construct representations. So what can we do? So this is a filtration, and it's actually filtration by normal subgroups. So what we can do is we want to start with this group here. Notice this group is just the same as this one, and we can just mod out by the next one. So let's do that. Let's mod out by the next one. What do I get? I get as the quotient just basically the matrices that have FQ on the off-diagonal and 0 on the diagonal, because only the off-diagonal changes, and O mod P is the residue field. And this is an isomorphism of groups, and if you look at this under addition. And so now we have to map this to something. So we can take a matrix and just map it to the sum, which just gives us an element of FQ. But I said we want an element of C star, so we just map this to C star. For example, if this is Q is P, so if we have the P roots of unity, we just map it to the, sorry, if this is P, so we have FP, we just map it to the P roots of unity here. And so now this composition from here over here, this is a map, this is a character that maps this compact open subgroup to C star. And this is the representation role that we were looking for. So now I've told you how to define a representation of this compact open subgroup K. Now we have to do the second step, which is the compact induction. What's compact induction? It just means we look at all the functions on G to see that as for normal induction, transform on the left via this row K. So if you have an element small k of capital K, it pulls out via this character row K. And compact induction means that the function should be compactly supported. And so this is an infinite space because it's basically the space of functions on G mod K, and G is SA2, K is a compact open subgroup, so this is an infinite space, and we act on it via right translation. And so this is an example of a supercuspidal representation. This here is a supercuspidal representation. This is a special example. It's actually an epipelagic representation, or even a simple supercuspidal representation that were constructed earlier by Gross and Reader. But in general, all supercuspidal representations that we know of are constructed more or less in the same way, except that this compact open subgroup K gets much more complicated. It's built out of a lot of Moy-Prasad filtration subgroups of different subgroups of the group, not just of the group itself, but of twisted Levy subgroups. And for each twisted Levy subgroup, you take a character, and then you put all the compact open subgroups together, all the characters together, put in a dip0 piece in the end, and then you get a representation via use construction. But as I said, it's slightly more complicated to make this precise, but basically the essence is you always have these spaces of functions. They're just getting more complicated. So I hope that if you leave this talk afterwards or just turn off your computer, you at least have seen one supercuspidal representation now and have an idea of how they look like. All right, so let me go back to just add a few more words to the general results before I move on to the number theoretic component. So as we have just seen, I gave you an example of how to construct representations. JKU's construction is more complicated, but still his construction is of the same spirit. He gets a compact open subgroup K, with a representation rho of it, that he then induces up to a G. And I've actually proven that his construction provides us with supercuspidal representations. But still, I said that unfortunately the key ingredients in JKU's proof are wrong because they are off by ±1. But for some applications, it would be actually nice if they were true. So there's an alternative to actually prove that JKU's construction works, which is the following result. And so maybe before I tell you the result, so the proof here that I gave that use construction works is basically taking half of use paper, so say 20 pages of use paper, adding 3 pages on my own to it. So it's rather short in total. The alternative that I proved together with Tasha Kalitha and Lawrence Spice, this would rely on taking all of JKU's paper, so 40 pages of JKU's paper, and adding on another paper by us that's maybe 30 pages long. So it's much longer. It's a much longer fix, but it has a lot of advantages that I show you on the next slide. So what did we do? We said, oh, the problem with JKU's propositions and approach was the ±1. So why don't we add in the ±1 to make JKU's proof work? So we show that there exists a character from this KU to ±1 such that U's main ingredients, proposition 14.1 and 14.2, are satisfied for this twisted representation, twisting U's representation, rho KU, with this character, this is ±1 character, this epsilon. And then we obtain that if we induce this, we can now use JKU's proof to show that it's supercuspidal. But so this is easier said than done. In order to construct these characters, we had a lot of restrictions. This is not just some ±1. We basically had, it's more complicated than that, but roughly the idea is that we had some possibly disconnected reductive group of our finite field, and we knew what the character had to be on all possible tori, and even more than that. And from that, we had to construct a character epsilon that restricts to the correct one on all these tori. But now you wonder why? Where did these restrictions come from? Why do we care about our epsilon? So our motivation is because this epsilon actually appeared so often beforehand in the literature. There have been so many instances where people, for example, tried to write down a local Langlands correspondence and had to put in an epsilon, a ±1, to fix it. Or where people tried to write down a character formula, had to add a ±1 and to fix it. And so our hope is that our epsilon, our ±1, will be somehow a universal fix to all these problems. So for example, Lawrence Spice has a paper in which he shows how to calculate Harishchandra characters of these supercuspidal representations. But this relied on assuming that there exists such a ±1 to fix everything. So we hope that as an application, we get finally character formulas, which is very exciting because then we can prove all kinds of other things. In particular, we can work with the local Langlands correspondence. But already to write down a candidate for the local Langlands correspondence for so-called non-singular representations, Tasha Kaletha needed also an epsilon. A priori, these two epsilon looks different, but now we've realized that these two epsilons can be actually realized by this 1 plus minus 1 that we found. So another application is that we can write down a local Langlands correspondence for non-singular representations. Another application is that we can prove that the local Langlands correspondence for regular supercuspidal representation. So that's a large class of supercuspidal representations, but one that's very regular. So it's even more regular than non-singular. So non-singular representations basically correspond to all those representations with supercuspidal Langlands parameters, and regular is slightly more regular than that. And in order to prove that this local Langlands correspondence satisfies all the properties we wanted to satisfy, like the character identities, we need this epsilon in there. And we hope there are also other applications. For example, people working with Hecke algebras, they rely on these results as well. All right, so let me pause just for a second. That's the end of the part that I wanted to tell you about the representation theory of p-adic groups, about these results. Now I want to move on to the second half, or not quite half, it's less than half time-wise, where I want to tell you how to use these local results to prove things about global results. So for this, we have to change a bit directions. I have to begin by telling you more about local results first, but we have to change a bit our viewpoint. So far, what we try to do is construct one supercuspidal representation very explicitly. What we want to do now is we want to have a global application, for example, that says arbitrary automorphic forms, whatever they are, I can tell you more about what I mean by that later, are congruent to particularly nice automorphic forms, where by particularly nice, I mean that they are supercuspidal at a prime, because that allows for a lot of global arguments to become much easier. So what we really want is we want to obtain some information about some representations by just studying compact open subgroups. And from compact open subgroups, we want to detect something is supercuspidal, but we don't actually need to know what precisely the supercuspidal representation is. And so for this, the theory of types is very helpful, but a relaxed theory of types. So in general, the theory of types is to obtain information about the representation of a group by studying representations of compact open subgroups. And you could do this, for example, by trying to construct supercuspidal representations, pin down the supercuspidal representations by knowing what the representation looks like on a compact open subgroup. But for our global applications, we only need to know supercuspidality and not what the representation is like. So what we need is so-called supercuspidal type. So what is this? Supercuspidal type is a pair consisting of K, compact open subgroup, and rho, a representation of it, similar to before, such that if you take an irreducible representation pi of the group G, you want that pi restricted to K contains rho, so the space of K homomorphisms is non-trivial. That should imply that pi is supercuspidal. So you want to detect supercuspidality by just restricting pi to K and look at, does this representation pi restricted to K contain the representation rho? So this is somehow weaker than asking that if you induce a representation, you get a supercuspidal representation. So what is an example? So you've seen the example of SL2 before, but now if we take K just to be this compact open subgroup without the plus minus 1 and take this representation rho from before, that's an example of a type, a supercuspidal type. Because every representation containing rho when restricted to K is either the representation I constructed for you before, or it is the representation that you can obtain using the same construction that I did before, where instead of sending the plus minus 1 to 1, you send the plus minus 1 to the sign character. So send it to plus minus 1. So this means this detects one of two supercuspidal representations, but we don't know really what. But so what do we really want? So I say it's somehow easier to find these types if we don't want to pick out one supercuspidal, but are happy with the whole family. But if that was all we wanted, life would be too easy. For global applications, the problem is that this K is rather large. And this rho is very complicated. I've showed you an easy example, and I said, in general, it's much more complicated than that. And for global applications, what we want is that this rho is just a character, because it's so much easier to check if something contains a character than to check if something contains a crazy 315-dimensional representation. And also, we want to prove congruences between automorphic forms. And we want automorphic forms to be of arbitrary level, in particular, very small level. So we want this K to be rather small. But for constructing supercuspidal representation, this K will never be small. In JKU's construction, K is always rather large. So we introduced the notion of so-called omni-supercuspidal types, which on the first glance, this might look very complicated. But why did we write this down? We wrote this down precisely with the global application in mind. So just think of it as that's what we need for the global application. The reason I'm writing this down is because maybe you realize this helps you to apply in your own work. When I gave this talk earlier, Emerton and Peshkunas were in the audience, and they afterwards came to us and said, oh, we have proven something that works for GLN, and we used the explicit representation theory for GLN. But your result is basically proving what we used for GLN in a much more general setting. Could we get the same results for general groups? And yes, that's the outcome. So we looked at the result of Emerton and Peshkunas, and it turns out we can prove the same for general groups using our result. So okay, I haven't even told you what the result is because I still need to tell you the definition. The result is that the objects that I'm defining exist, that a plethora of them exist. So what is the definition? The definition is that an omni-supercuspidal type of level p to the m is the following. It's a pair consisting of U, a compact open subgroup as before, and lambda. What is lambda? Lambda is a character, but it's a character from U to Z mod p to the m. So it's valued in Z mod p to the m, not in C star. And I want to get supercuspidal types out of this. So how do I get a character out of it? I can compose this with an arbitrary character psi from Z mod p to the m to C star. And I want this character to be non-trivial. And then I want that for every psi that's non-trivial, I want that the pair consisting of U and this psi composed, this lambda composed with psi, is a supercuspidal type. So I don't just want to have one character that does it. I want for all psi's to actually give me supercuspidal type. So this is much more difficult than to just find a character, because this psi, it might just map this Z mod p to the m just to the p's roots of unity. So it might lose a lot of information. And we still want it to detect supercuspidality. And as I said, the reason we use this definition is because that's what we need in the global application to detect supercuspidality. This is what appears somehow naturally when studying automorphic. So you don't have to remember this definition, just remember this is what we really need. And the result is that actually we have plenty of them. We have all those we need. More precisely, assume that the group G splits over tame extension as before. I also assume now that the characteristic of the local field is 0 and that P is larger than the Coxeter number. This is just for technical reasons, because I believe in the end we can do it for all primes, but at the moment we rely on all the theory that I introduced in the first half, which still has the condition that P is greater or doesn't divide the order of the Weyl group. So assuming that P is greater than Coxeter number is just adding a bit more strict condition just to make our life easier, because eventually, I think we should just do it for all primes. So under this assumption, there exists a sequence of these UM lambda m's, such that these UM lambda m's, these are omni-supercuspidal types of level p to the m. So these are these nice objects up here. And these compact open subgroups, they are normal subgroups that become smaller and smaller and smaller. So they form a basis of open neighborhoods of the identity. So that means if you really want to work with automorphic forms, of arbitrary type, of arbitrary level, you can take this U to be as small as you want. You can get as small as you want. So that's why this is much more difficult than just constructing types, because first of all, we have this lambda in here that composed with all psi's should detect supercuspidality. And these are becoming smaller and smaller and smaller, these compact open subgroups. And once we have this result, Why do we care about this result? It's what I keep telling you, because of the global applications. So let me first formulate it just roughly. So the global application is that we obtain congruences between arbitrary algebraic automorphic forms and those that are supercuspidal at a prime p. I'm making, if time allows, I make this more precise later. Similar and second application is, I'm just writing this down in case someone is interested in, and also to advertise that this following the second result just arose by Emitel and Pashkunas attending our talk and realizing what they did for GLN with our input, we can do this also more general. And so the result is that classical automorphic forms that have a fixed weight and that are in addition supercuspidal at prime p are dense in the spectrum of a Hacker algebra, where you use the approach by Emerton using the completed cohomology. Don't worry if this doesn't mean too much to you. As I said, it's also meant as a motivation that if you can prove something where you use heavily representation theory of GLN, maybe together we can prove it for general groups. And again, so this might be a bit vague. What do we actually get out of this? So one possible application is the following slogan, which is still vague, and I make it more precise afterwards. The slogan is that we may assume that an automorphic form is supercuspidal at a prime p. And automorphic forms that are supercuspidal at some prime are much easier to work with geometrically. Okay, let me give you now an explicit example, not just broad slogans. How can we use this? And I hope you find many more applications, but one example is the following. If you look at the global Langlands correspondence for GLN, what is the global Langlands correspondence? The global Langlands correspondence is the idea that you start with a nice automorphic representation, say of GLN, and I need to put an assumption here. I put the assumption here that this pi is essentially square integrable at some prime. What does it mean? Essentially square integrable actually is, is implied by being supercuspidal. So essentially square integrable means that the matrix coefficients, up to center, the matrix coefficients are square integrable more or less, and supercuspidal means that they are compactly supported. And so I said this is this assumption supercuspidal at a prime. So it means this representation is a representation of GLN over the Adels. So it's a restricted tensor product of GLN over QL for all primes L and the infinite component. And if you look at QP, you want this representation to be a supercuspidal representation of GLN of QP. And taking such a nice automorphic representation, in 1991, Clauzel constructed the global Langlands correspondence for it, which means Clauzel provided a Galois representation with QP bar coefficients that is attached to this representation. And I should say, I mean, later this got refined, like Harris and Taylor put in a lot of work to refine this. And what can you do now with our result, with our applications, either one or two? You can remove this assumption. You can remove this assumption here about the square integrability by basically saying that those that are not square integrable are congruent to those that are square integrable, and then you use the congruences to build the Galois representation over here. So that's a very explicit application. So I mean, I should say, we are not the first ones to do this. This result, this removal of this condition has been obtained much earlier by work of Shin, Clauzel, Harris, Labesse, and Genevieve Harris, but they all used very elaborate geometric and endoscopic arguments and eigenvarieties, and it was very complicated and very specific to this case of GLN. What we do now is we just use our local results and basically plug them in to remove it. And the advantage is that our global results, like the theorem 6 of the previous slide and these applications of it, they hold for general reductive groups, or at least the global results hold for general reductive groups that are compact at infinity. So that means that we hope we can use the same results to remove such assumption also for other groups. So people are trying to write down global Langlands correspondence beyond GLN, but it's very difficult to do so. And basically what our result tells them is that they could just look at automorphic forms that are supercuspidal at a prime and that are therefore much easier to work with geometrically. So we hope that our result can be used to construct a global Langlands correspondence for more general groups and push this field beyond the current state of the art. All right. I think, okay, now I have a problem. I started a bit late, but I was supposed to go for 50 minutes. So what I would do next would be to actually state the precise result about the congruences, which would take up another few minutes. But let me maybe stop here, and if anyone is interested in it, I can always tell you about it, and I shared the slides. So let me stop here. Thank you very much.
Let's thank Jessica.
Oh, I should do one more thing. I would like to also advertise a postdoc position in Cambridge, whose application deadline is today. So if you're interested in a postdoc, please consider applying. The reference letters can come in later. Just you need to put in the application today. Sorry.
So are there questions for the speaker?
We just shut.
There was a question. Or you can unmute yourself.
Well, if I can, sorry. So these omni types and so forth, you say there exists a sequence. I was just wondering, so do there exist, gobs of these sequences, and does every type contain the tail end of one of your omni types?
There exist a lot of sequences, but not every type contains one. Basically, the ones we construct are particularly nice. We call them we construct them from what we call one-toral data or zero-toral data. So they are in some sense corresponding to toral supercuspidal representation, except it's not well defined what a toral supercuspidal representation is. So they correspond, so since you know JKU's construction, they correspond to the case where there's smallest twisted Levy subgroup, which JKU denotes by G upper 0. This is a torus in our case. It's an anisotropic torus. And they are constructed from particularly nice JKU data where the smallest piece is an anisotropic torus.
And do you have some hope is there any need to go back and do it for other twisted levies, or?
So so what we want is that if we just take a character, it should detect supercuspidality. And if the smallest twisted levy is not an anisotropic torus, in general, a character will not suffice to detect supercuspidality. So the types that you might get types that correspond to different blocks, but not all supercuspidal. I mean, no, you shouldn't. So what you can, for some supercuspidal types, using this approach, it's impossible, okay, let me reformulate this again. There are some supercuspidal representations where you cannot detect their supercuspidality by only looking at characters. You need more complicated representations.
Thank you.
So if are there other questions for the speaker again? If not, we should thank her.